periodic table with looking at the Bohr model. Okay, so actually Niels Bohr created this model to depict where the nucleus was located and where the electrons actually were located on the outside of the nucleus. And so on this Bohr model, it is a drawing of electrons found in the shells as we had seen to the diagram to the right. Okay, so let me get this up and running. There you go. And so components that you find in the Bohr model basically are those circles, and they represent the rows where the element is found on the periodic table. And the dots represent the number of electrons. So the first circle has the first circle closest to the nucleus, the inner circle, actually has a maximum of only 2 electrons. And the second on past, the maximum number is actually 8 dots. Okay, so here we're going to model and draw oxygen so you have an idea, and then we'll practice in just a second. So I'm going to start with drawing a closed-in circle to represent the nucleus. And oxygen, if I were to look on the periodic table, it actually is found on the second row. Therefore, I'm going to draw 2 circles. Okay? Now, the other thing I'm going to do, I'm going to draw oxygen. Basically, its atomic number, the number on top, is actually 8. So that means I need to place 8 electron dots on here. Now, the first shell can only hold up to 2. So that's the maximum number. So then the remaining are actually going to be on the bottom shell, or on the outer shell. So I'm going to draw the first 2 dots to represent those 2 electrons right there. And then what we have is, if I take 2 from 8, I get 6. And so that leaves me to draw 6 dots on the outside with oxygen. Now, another way to look at this is if we go back and take a look at my items with the configuration there, with what we were saying with the valence electrons. Oxygen is in the 6th column, 6A. So therefore you follow it up, and then it would have 6 electrons in the last shell. So let me make sure I have 6 in the last shell. 1, 2, 3, 4, 5, 6. So here is the Bohr model of oxygen. Let me darken that one right there. Okay, and let me back up just on this periodic table. So this one right here is labeled 1A, and that means it has 1 electron in the outer shell. This one's 2A, so it has 2 electrons in the outer shell. 3A right here, we're going to bypass those in the middle. We're not going to worry about those right here. All of these right here have 3 electrons in the outer shell. 4A, 4 electrons in the outer shell. 5A, 5 electrons in the outer shell. 6A, 6 electrons in the outer shell. And 7A, okay, in the outer shell. Oops, sorry, let me make that better. 7 right there, 7. And then this one right here, the last column is 8A in there. All right, so let's continue practicing right here. So let's look at neon, okay, and let's practice those. So neon, we're going to start with drawing the nucleus right here. Neon is found in the second row, so we're going to draw 2 rings, 1 and 2. Yay, I drew that a little bit better. All right, so neon, when I look at it, has an atomic number of 10. So I'm going to write 10 up here to kind of keep it in point here. Okay, so remember, the first shell can have a maximum of, on here, only 2. So I'm going to go ahead and place those 2 right there. Okay? So when I take 2 away from 10, I get 8. So therefore, we're going to place 8 in the outer shell. So I got 1, 2, 3, 4, 5, 6, 7, and then 8. Okay? Now another way, look at neon, follow it all the way up, and it's found in the very last column where I have 8A. Okay, so that 8 tells me there are 8 electrons in the last shell. Okay, boron, let's practice that one. Boron has an atomic number of 5. So remember the first shell. Boron's also in the second row, so we're going to draw 2 shells to represent that one. And so remember the first one has a maximum of 2. So we're going to draw that right here. So I have the 2. And then if I take 2 from 5, I'm left with 3. And also if you follow boron all the way up, it has 3. It's in column 3A, so therefore it has 3 electrons in the outer shell. Okay, helium is the last one. I'll draw a dot. It's in the first shell, so therefore I will draw only 1. And remember, how many are in that first shell? Think about it. What did I draw right here? Only 2. So remember, the maximum amount is 2 in the first shell. Okay? All right. Now, the electron dot diagram basically describes how many electrons are in the last shell, and you draw it with the symbols. Okay? So let's practice. We're going to start with neon. So what you need to do is start off with writing your symbol. So I'm going to do neon. Okay? And neon has 8 electrons. So basically how you start off is north, south, east, and west. That takes care of 4, but there are 8 electrons in the outer shell. Remember, it's in column 8A. So it's 8 electrons. And I got 4, so we're going to start again. North, south, east, and west. So therefore, that is how you draw the electron dot diagram for that particular one. All right, now let's practice some more. Let's start with fluorine. Okay, so fluorine, we're going to write the symbol. Now fluorine is found in group 7A. That means we're going to draw 7 dots. So again, we're going to do north, south, east, and west. That's only 4. North, south, and east. And that takes care of 7. Okay, sodium is Na. Sodium only has 1 electron. It's found in 1A. So it has 1 dot. So you just put it on the top under north. Carbon is in group 4A. So you're going to do all the north, south, east, west. North, south, east, and west. And there's your electron dot diagram. Now, elements that are found on the periodic table, when you look at this diagram, we basically are classifying elements as either metals, which is the biggest group, they're in green. Then you have nonmetals, which are in orange. They're to the far right. Metals are on the left, except for that hydrogen. Hydrogen's a gas, and the only reason why it's paired over here with this group in 1A is due to the 1 electron that it has. So it's kind of placed there by default due to that reason, but it's technically a nonmetal. And then these right here on the purple are called metalloids, and metalloids are basically those elements that have properties of both metal and nonmetal. And here are some properties of metals. They're the largest group. They're on the left. They're good conductors. That means electricity is going to flow through it. So think of copper and your pots and pans. If it's ductile, here's a term. That means I'm going to form it into a wire, just like this picture up here. Luster means it's going to have some shine. It's going to reflect light. Malleable means I'm going to take this hammer over here and I'm going to hammer the metal into a shape. And francium is by far the most reactive metal, and it's at the bottom of group 1A. Nonmetals, their properties, it's dull, it's brittle, it can break easy. They're poor conductors. Most of them are gases. Most of them are found on the right. And fluorine, which is on the right side, is the most reactive nonmetal. Metalloids, when we look at them, have characteristics of both metals and nonmetals. And they're found on that little step, and we call it the stair-step line. It's a black line that divides the metals from the nonmetals. And here list all the this lists all the metalloids that are found on there. Okay. Now there are some periodic trends, and one that's kind of cool is the reactivity. So as you move from the left side of the periodic table all the way to the right side of the periodic table, the ability to make reactions kind of decreases. They're more reactive on the left side and they become less reactive on the right side. And size, as you move down, think of it, the rings. I'm going to create and build more rings. I'm going to draw more rings. So therefore, because of the row it's in, therefore, it's actually going to increase in size. But as you move from left to right, they're going to decrease because they're being pulled in towards the nucleus. That positive and the negative charges are actually pulling it in. So as you move from left to right, it kind of shrinks in size, but as you go down, it gets bigger. Okay? So we're going to stop right here for this segment, and thank you very much.